Hello, and welcome to Urbit Developer Calls. We do these every 2 weeks, and we've got a pretty exciting one for you here today with Edward Amsden, or ritpub-sipsyl, who you've probably seen around. Now, he's been working through the grants program for a while now on a project to bring WebRTC support to Urbit, which is pretty exciting. We'd actually been talking about this specific project and the need to get this support into Urbit for a long time. And very happily, he, after having done a bunch of research into WebRTC and trying to wrap my head around how it even worked in the first place, he showed up with a proposal that was basically complete as a more or less an expert that just knew how to do this, which was a little bit of Urbit serendipity, which actually happens pretty often. And it's been an absolute pleasure working with the guy. So without any further ado, here's Edward.
Hello.
Edward, welcome.
Thank you.
So yeah, I'm curious to know just, if you could introduce yourself and hear a little about you and your background and what brought you to Urbit.
Yeah, so I've been doing software for, I finished up undergrad in 2012 and was programming even in high school before that. And then I first heard about Urbit when I was in grad school at Indiana University, and one of the undergrads there had gone to work with Curtis and Galen at Tlon for the summer and came back in the fall and all excited and was telling us about it. And I was more than a little bit skeptical. There's a new programming language, two new programming languages, one like compiled target language that's run by just pattern matching C functions. It's, being a grad student in compose, I was like, there's no way this actually works, right? And so I didn't really give it much thought at that point. And then probably about late 2018, early 2019, I started seeing sort of rumblings about Urbit on Twitter, and looked into it a little bit more and was like, well, they've, to my surprise, they've actually got something up and running here. And the more I looked into it, the more I was like, this addresses a lot of the things that as a software developer I've grumped about computers for years. So late last year, I bought a Planet, jumped in and started playing around. Back then you could buy a Planet without emptying your wallet in gas fees.
Yeah.
So I just bought one and jumped in and started playing around. And when I read a little bit about the communications that Urbit facilitates, I said, well, you could use this as a signaling channel for WebRTC, and then you would have video calls. Wouldn't that be neat? And then I saw you guys had a grants program. I was like, and I could actually get paid to do this maybe. So
yeah. Always a good thing.
So yeah, that was more or less how I wound up here.
Yeah.
About 4 months now after the grant started.
Okay. And how's how's that process been?
It's been really fun. So I started out, I was like, well, I'll make a smaller, easier proposal. Because of my day job, I do a lot of Haskell programming, but also a lot of Nix-based software deployment. And said, well, Urbit's already built with Nix. It'd be fairly easy to get a good Docker image out there. So I did that first. And that sort of got me comfortable with the grant process. And I think I submitted the WebRTC proposal at the same time, but I did the work for the Docker one first. And then, it's a lot of fun. It's something where if you can work by yourself and push yourself to set your own deadlines, then it's the right sort of work to be doing. And there's it's a lot of fun to be in at this stage of Urbit as well, where it's not really very nebulous anymore, but it's also not, you're trying to catch the bandwagon that everyone is already on. So this is a really fun, exciting time in Urbit development.
Yeah, I couldn't agree more. There's a ton of exciting things that have been going on lately. I mean, just 2 days ago, we were demoing the Bitcoin wallet, which started through the grants program. Now we're doing this. We're going to have a town hall event in about just a little over 20 days, which should have, an exciting lineup of speakers. Some of that will be development related, some broader related. There's just, there's just a ton going on, which is really exciting. And question, one I have and one that came in from the audience as well.
Yep.
What is that behind you?
That is, I found that on Wikimedia Commons this morning, but that is how telephone calls were originally connected. So when in real old movies, if you say, operator, can you connect me to, the operator was literally unplugging you from their own headset and plugging you in to someone else's telephone with an audio patch cable. So that is a very old style telephone switchboard that I have as my background.
Sweet. Well, I think that's actually a pretty good segue into the main talk here. There's a component that you built called Switchboard.
That's correct.
Yeah. So let's talk a little about WebRTC and go over how this thing that you've built actually works. All right, here we have a little presentation. Then I'm going to drop off.
Okay, thanks, Josh. So I'm going to talk about the state of WebRTC on Urbit and also how this thing has been built, how WebRTC ties into Urbit, and what you can do with it right now. So we should start off a little bit with what is WebRTC? What you might be familiar with it. You've almost certainly used it in a user capacity, but WebRTC, the sort of the pitch for it is video calls in the browser. But the technology is actually more general. It starts off with a protocol specification that specifies how peer-to-peer media streaming between browsers is to work. And also other programs can implement this, so you can have other software talking to a browser over media. But it also gives you a browser API specification. So it gives you a JavaScript API that you can use in the browser that gives you two things. It gives you media device acquisition, which we're not going to talk very much about today, and peer-to-peer channel setup and interaction, which is primarily what we are going to be interested in. So if you want to build an application using WebRTC, if you just want to pick up WebRTC and start building with it, you're going to need a couple of things. You're going to need some ICE servers. So ICE is Internet Connectivity Establishment. This is how your browser is going to determine how other peers can connect to it. This is if you're behind, whether you're behind a NAT or you're actually browsing from a device with a public IP, your browser is not going to look at your network interfaces and broadcast those addresses to the world. It's going to talk to a server and find out what its public internet address is. You're also going to need what we call a side channel for SDP messages. An SDP is Session Description Protocol, and this is how your browser is going to tell your peer's browser and vice versa where we can connect and what kind of media we're exchanging. So this is going to handle both connection negotiation as well as media format negotiation, bit rates, things like that. And then you're going to need the media or data that you're going to be sending to your peer. Again, that's not the primary focus of this talk today. We're going to talk about the other two parts. If you have all these things, then the RTC peer connection interface, which is sort of the main entry point into the WebRTC API, will give you data channels that you can send messages back and forth on. and it will give you media stream transit. So you can get a hold of a media stream object in JavaScript from your webcam from somewhere else, hook it to RTC peer connection, and send it to your peer. And then your peer will have a media stream on the other end. So I have built a system called IcePond that helps you to get a hold of ICE servers in a programmatic way, and a system called Switchboard that handles call setup, call hang up, and this side channel for SDP messages so that your browser peers can connect. So we'll talk about ICE servers a little bit first. And these, again, help us answer the question, where are we going to send packets? The answer is we're going to send them where our peer tells us to. This is, again, a bit of a chicken and egg, but we'll get there in a minute. But it asks the reciprocal question, where do we tell our peer to send packets? So what's our public internet address? There's not really an easy programmatic way to discover, am I on a private network? Am I on a public network? And especially if I'm on a private network, I don't want to be broadcasting the structure of that private network to the internet. And also, what is our port on our public internet address? So if I initiate communication outbound through a router, network address translation router, it's going to map a port on the public IP address to my private socket. But there's not an easy way without some external coordination for me to discover what that is. So the solution that WebRTC and other systems that use ICE goes for is, first of all, something called a STUN server. And STUN stands for Session Traversal Utilities for NAT. And it's very simple. You send a STUN server a UDP packet in a certain format. It sends you one back where the body of the packet essentially consists of, you are talking to me from this IP and port. So this is sort of a programmatic version of going to DuckDuckGo, typing in what's my IP and getting that back, except you also discover your port as well. There are situations where this breaks down, and the primary way that this can break down is that your NAT router may only map that port for one destination and responding IP address. So if you go talk to the STUN server and that opens the port on your NAT, that port may only be open for the STUN server and nobody else. So to get around this, really at some point we have to fall back to relaying, where we can connect again to a server that we call a turn traversal using relays around NAT. And it will give you an IP and port for itself that your peer can send messages to, that it will relay to you. So this is how you can get an IP and port that your peer can communicate with you on. And a little note here, the WebRTC documentation, other stuff that involves NAT traversal very often discusses ICE servers. This is either a STUN server or a turn server. There's nothing that's just an ICE server. There's no separate server. ICE servers are either STUN or turn servers. So we need one of these servers, or one or more of these servers, running out on the public internet. And we need to let our application know which one to contact. So how are we going to discover these? If we're building Google Meet, or we're building Jitsi, or we're building Appear.in, Facebook Messenger, any of these other centralized products, even though our video is going to go peer-to-peer, there's still a central server coordinating this, so our central server can tell us what ICE servers to use. And that works fine in that use case, but this is Urbit. We don't have one central server to share all this from, so that won't work. We could hard code them into our application, and now it could be the app developer's responsibility to make the ICE servers that are hard coded in the application run in perpetuity. I don't want that responsibility as an application developer. I don't think any other application developer really wants that responsibility. We could just make the users configure their own ICE servers. I don't think this is a good idea either. So what we can do is do what Tim Liptev referred to as commoditizing the infrastructure. We can have certain nodes host servers and have users configure how they will discover servers with some sensible defaults. So the default that IcePond works with right now is that it will ask your sponsor for ICE servers. It also uses a publicly hosted one run by Google for now, a Stun server, but there's no really open public turn server. So this is still going to be necessary to expand to the case of a lot of people who have home NATs or any carrier NAT for a mobile device or corporate routers where you have this issue where you need relay. So the idea here is that infrastructure providing nodes, especially stars, can advertise ICE servers as part of the infrastructure they provide to sponsored planets. So this is our answer to where do we get the ICE servers that we need for WebRTC. We also need to be able to signal out of band between the two peers to be able to set up and tear down the call and negotiate the connection. So this encompasses several questions. I have an app. How does my app know that someone else is trying to call me? How does my app tell the peer, as you're setting up the call, where to talk to, where to send the media? Again, the usual answer when you're building a WebRTC application is you have a centralized database of calls that ties a call ID to a couple of peers, and peers send SDP messages to this database, and then they get it down the other end through an HTTP event source. Again, this being Urbit, there is no one centralized database. We need a peer-to-peer exchange of messages between our two ships. So the structure of this is going to look like my application is going to talk to my Switchboard agent. We'll talk about Switchboard in more detail on the next slide. My Switchboard agent is going to talk to your Switchboard agent. So this arrow in the middle is the ship-to-ship communication. And your Switchboard agent is going to talk to the instance of the app that you are running. So Switchboard gives us the functionality of call setup and call teardown and SDP relay. It provides a poke that you can give it to initiate a call. It provides a route that your application, or a path that your application can watch to be notified of incoming calls. Once you're setting up a call, it provides another poke that you can send it to pass along any SDP messages that you need to send to your peer. And at the other end, a path that you can watch to receive SDP messages from your peer. So this is all the Urbit side of things. IcePond and Switchboard are two Gall agents. They run on Urbit. They handle all of the ship-to-ship communication that you need in order to discover ICE servers, in order to actually set up a call with your peer. But WebRTC is primarily used in the browser. So we have browser-side, JavaScript-side interfaces as well. We have a Node.js package called IcePond that lives in the IcePond.js directory in the repository. This provides one class, IcePond, that will just get ICE servers for you as they're discovered. We'll talk about more how these things are used after the demo. This is just an overview of what is provided. And then for Switchboard, again, we have a Switchboard Node.js package in the Switchboard.js directory. This gives you an WebRTC app class. And this is a factory class that lets you make and receive calls. And when you make a call or when you receive and accept a call, you're given an instance of WebRTC peer connection class. This is an extension of RTC peer connection, but the SDP signaling is already implemented for you. All of the event handler that you have to write to whenever RTC peer connection needs to send an SCP message to send it over your developer implemented side channel, already done. All of the watching for need to renegotiate when new media is added, already done. All of the need to renegotiate for new ICE servers, already done. So this is going to give you the ability to just set up a call, hook up your media stream or your data channel, and go. And if Josh is here, we're going to give a demo. This is a chat application over WebRTC. So these chat messages that you're going to see are going to go over a WebRTC data channel straight from my browser to Josh's browser and back.
Yeah. Now you're going to have to hang on one sec.
Yep.
So this software that we use, StreamYard, to broadcast this, it's only lets you put one screen on at a time. So we've come up with a very, I wouldn't quite call it elegant, but way of, let's see here, showing what we're doing here. Okay, there we go. Bear with us.
Do you still need to log back into your ship, Josh?
Yeah, I do. So go ahead and explain what I'm doing here.
So Josh has the Urchat FM application running in React development mode, and he has a Moon set up that's running IcePond and Switchboard. So he's just going to authorize the app and create an airlock from his browser into that Moon. And that's up and running. So now I can come here and I have his Moon's @p filled in here. And I can click call. And in short order, we see call from. And if he clicks answer, our send buttons will enable as soon as the SDP negotiation completes, and we can chat with each other. Again, these chat messages are going over WebRTC, over a data channel. These are not flowing through Urbit. These are flowing directly from my browser to his browser over a UDP connection. And this same kind of connection is exactly the sort of thing that you'll be able to send audio, video, other kinds of data. These are just sent as strings, but you could send JSON or anything else over this. So if you want to implement video games or file transmission, there's all sorts of things you could do with this straight from browser to browser.
Yeah.
Okay.
So there we go. It works.
Yeah. This is
2 for 2 on live demos this week. It's a miracle.
Yeah. And again, I want to emphasize that Josh and I are both behind home NATs. Neither computer here has a public IP address. These browsers are both running, and yet we're doing direct peer-to-peer communication. And our Urbit ships helped set that up, sent the messages back and forth to help set that up.
That is right. Okay, let me come back here. I'm going to remove that guy, and then we'll go back to your...
If you could put the slide. Okay, so Josh, can we make the slide? There we go. Okay, so that was pretty neat. So if you want to write a WebRTC app using Urbit, there's not a lot that you have to do. You need to set up an Urbit airlock. You can use the Urbit/HTTP API library that's in the Urbit repository and also available with this package name through the Node package manager through NPM. And then you're going to want to create an WebRTC app instance using the Switchboard package that I mentioned earlier. And provide this airlock instance to it. You're going to want to register a handler for the incoming call event. So this is just a standard JavaScript event handler. And the event that you'll be passed in the event handler has two methods. You can call reject and say, no, I don't want this call. And the other side will be notified that you hung up without accepting the call, so they can handle that in their call flow. Or you can call answer, and this answer method will return a peer connection, an instance of RTC peer connection that will automatically start negotiating. And then once you've set up this handler, you want to call the initialize method. And we do it this way so you can have your handler set up before it actually starts talking to your ship. And then for your actual call flow, again, it's not very difficult. You can place calls using the call method from WebRTC app, and you'll get back a connection that will start negotiating as soon as the other side accepts the call. Or you could start with one that you obtained from calling answer on an incoming call event. And then from there, you're going to want to create an instance of IcePond. You're going to want to register a handler for ICE server events that will add ICE servers to the peer connection. This is actually done through the configuration attribute of RTC peer connection. And then you're going to want to add your media or data streams. Once you've done all this, you could call initialize. You can actually add streams after initialization as well, and it will renegotiate. Both on the IcePond instance and the peer connection, you want to call initialize, and that will start the process of getting ICE servers and handing them off to the peer connection, and the peer connection actually starting to try to negotiate. And that's basically it. So what do we have here? What have we built here? What's the potential behind this thing that right now we can chat browser to browser on? Well, we have a WebRTC library. There's a couple of those out there, but it commoditizes external infrastructure dependencies. There's not a hard-coded set of servers. You, as the app developer, don't have to run a server. It unifies personal identity and addressing. This is the killer app of Urbit. This is what we saw in the Bitcoin demo a couple days ago. This is what we're seeing again here. When you call that call method, you don't pass any sort of weird identifier. You generate an ID for the call to distinguish it from other calls between the two peers, but you say, I want to call WebRTC ritpub-sipsyl. You give the @p that you want to call, and that's it. And it removes the centralized coordination for call negotiation. We already have a peer-to-peer network. It already works. It's called Urbit. We use that for the channel to set up peer-to-peer media calls. So from this already built peer-to-peer network, we can bootstrap other kinds of peer-to-peer communication for more specialized purposes. But I really want to go back here because this part that I've highlighted, again, you're going to hear about this over and over as we talk about Urbit. This is really, really important. Any other WebRTC library that you use, you're going to have to go to put your users through some kind of authentication flow to authenticate them with a centralized server to prove their identity and to match them with call IDs that you're actually signaling. You don't have to do this in this case. Urbit takes care of, I have an @p, where do I send messages to? You just send the negotiation messages, or actually Switchboard sends for you the negotiation messages to that place. And so you can just call someone by their personal identity. The identity is a primitive that Urbit and the library give you, and you don't have to worry about it beyond that. And that's what I have for you today, and very happy to take questions at this point.
All right. Well, I'll echo everyone else in the comments section in saying that this is absolutely amazing. So well done.
Thank you.
Yeah, so I think there's a couple questions coming up just about whether or not we're going to be making those instructions you just showed into a how-to. But I think a broader question perhaps is like, what's the roadmap for what you're working on here? Where are you at in the process? Where are you going? And when does this become something that is really commoditized and everyone can start building on?
Right. So I would say that the Gall agents themselves are in pretty good shape. They're not the flow, the setup flow for Switchboard is kind of complicated, but it's mapped out. You could go look at the flow chart for how it works, and there's not a lot that needs to change about that. It's highly unlikely that there's a serious bug in that spec. And we've seen it work all the way from making a call. We didn't show this in the demo, but I can actually click hang up and the UI will vanish from Josh's side as well. And so all of that works already. And so what I'm working on next is the actual, what people are kind of excited for is the media calling part, where we take this, we have an RTC peer connection that's set up to signal between two Urbit chips, and now we'll hook your webcam and your microphone up, and you can call someone via Urbit and have the kind of conversation that Josh and I are having right now. You can call several people via Urbit and have everybody in a group chat, and or you can allow people to connect and stream media to them. They have a one-way, but one-to-many media stream. All of these are things that I'm going to be building for the second milestone of this grant, and that's just getting started right now. The how-to should definitely happen, and probably will happen as part of milestone 2. The code exists, it's documented. There isn't a point in the documentation that says do this, then this, then this, then this to do a call, but there should be. And that I won't consider the project done until you can do that.
Yeah. Okay. That's good. We've got. Okay. Let me scroll back up here. So there's one. There was a question a while back. I just want to make sure that this is totally obvious and driven home that we should maybe talk about. How is it peer-to-peer if it's depending on stars for the ICE servers?
So here's the thing. Just like the Bitcoin stuff, you can get your ICE servers from your star, or you can pick, if you have a NAT router that works with Stun, you could pick one of the ICE servers that's on a public list out on the internet. You can run your own ICE server in the cloud, and you can set it up so that's what you use, that's what your moons use. You could set it up so you offer it to other people, and they just have to configure to get it from you. ICE servers are going to be necessary as long as we have NAT on the internet. It's about the only way you can reliably set up peer-to-peer communication. And actually what Urbit is doing with stars in terms of how Urbit communicates is some of what Stun and Turn do. It's the same idea where the IP and port that your star or galaxy advertises to other ships to find you is just what they saw. And if that doesn't work, then they relay for you. So they're basically doing Stun and Turn for you, but the protocol doesn't match what WebRTC expects. So the solution is whoever wants to on Urbit can host ICE and Stun and Turn servers and advertise them to the rest of the network. So so there's no centralized dependency everywhere, but just like Urbit itself, it's not a flat anarchic peer-to-peer network. It's hierarchical, but also allows you to pick up and go somewhere else if you want.
And to be clear, it doesn't have to even be a star.
Right.
You run from one of these from your planet and
right.
advertise that. Right.
Right.
Anyone with a node can run an ICE server.
Yeah.
On it.
The only reason for saying star there is that the default discovery method that IcePond uses is ask my sponsor. Mm-hmm. Right. That's if you could change that configuration, just I think in the docs for IcePond, actually, there's a generator, so you can run a command very simply in your dojo and say, I want to do this for discovery instead.
Yeah, that's right. And I think the really, the thing about this model that's really cool is it encourages a proliferation of many people running Sun servers, because it provides a really good interface for a group of decentralized servers to all interface with those in the same way that our Bitcoin work is going to encourage a lot of people to run full nodes and ultimately add a lot of full nodes to the Bitcoin ecosystem as well.
Right.
Sweet. Okay, so a few other questions that have come in here. Let's see. Can this be interfaced with my own WebRTC infrastructure?
You can write any WebRTC app you want on top of this. If you have a non-browser WebRTC setup, then yeah, you could use, there's Urbit Airlock libraries for Rust and several other languages. So you could use that to talk to IcePond and Switchboard. I haven't written nice interactive libraries for Rust or anything other than JavaScript at this point. But yeah, you could have, if you have something that's going to muck several streams for you and make a more centralized WebRTC app, but you want to hook that up into Urbit, then you can do that. Anything that can talk to Urbit and can talk to WebRTC can use this stuff.
Yeah, that's right. And all these stun servers that are going to be running.
Right. And that's another thing to point out.
Yeah.
The stun and turn server advertisement functionality is separate from the WebRTC stuff. There's other applications that are not WebRTC that use stun and turn servers. A lot of video games use stun and turn servers to set up peer-to-peer connectivity. So any application where you need peer-to-peer connectivity, you can airlock into Urbit and use IcePond to get a hold of some stun servers and use those, and you don't have to touch Switchboard at all if you don't want to.
That's incredibly cool. I know we have a lot of people in the comments that are interested in seeing gaming on Urbit and on top of this infrastructure developed. So that is good to hear. For video chat, is the plan to integrate Jitsi or go some other route?
The plan is more or less just, I already have an RTC peer connection. It's very easy to get a hold of a media stream from the camera, hook it up to an RTC peer connection, and then at the other end, pull it out of an RTC peer connection and stick it in a video element. That's the easy part of WebRTC. What I've just showed you is the hard part of WebRTC. So if I find some nice, I haven't actually looked very much at what exactly Jitsi offers. If it offers a nice ready-to-go UI that you just have to hand it an RTC peer connection, then yeah, that would be great, and that will save me a lot of work. But I haven't decided exactly how the UI side of media acquisition and media display is going to work. That's coming up.
Yeah, awesome. Also from Ted. You think that an Urbit-based podcasting application like Gumroad, should that use WebRTC, or is HTML5 audio and video streaming? Is that a better option?
If you're going to be recording a podcast and then publishing it, you could stream it over WebRTC. That's not but the thing is, every peer is going to need to stream it from you. I think for something where you have an audio or video file ready to go, something where you host it on IPFS or something like IPFS or even S3 for now, and have your Urbit ship tell other people where to find it, is better for that case.
Mm-hmm.
For something where you want, like what we're doing right now, where I want to give a live streamed presentation, a live stream talk, a live stream performance, I have exactly this application in mind as one of the things I'm going to be building for Milestone 2. Perfect.
So before we go into the next question, something I think that might be relevant to talk about here is turn. What's the story behind turn, and what are the limitations to stun? Because really, we've talked a lot about stun so far,
right? So stun is two things. It lets you open. I've seen it referred to as a pinhole in your NAT, and it lets you discover the external address of that pinhole. So your NAT, most of us have probably at one point or another had to go into the web interface for our home router and open a port for something. Mm-hmm. But your NAT actually does this automatically all the time. Anytime it's not just a server that has a port, client has a port too. So anytime you connect to a web server, you have an outbound packet that goes to that web server's port, and your NAT notes that and opens a port that it fills in the reply address, and then it keeps track of, well, I opened this port for this port and this IP on the internal network. So Stun takes advantage of that. You send out a UDP packet, and Stun sends you a UDP packet back, and now there's this port mapping. And if your NAT is the right kind of NAT, which most modern quality home NATs are, that's a lot of qualifiers, right? Home modern quality NATs are, then that port mapping actually exists regardless of what public IP is trying to talk back to you, not just the Stun server. So now you can tell someone else, hey, talk to me on this IP address and port. And as long as packets keep flowing, usually like within 30-second intervals, then that will remain open and you can talk directly peer-to-peer over UDP. There's a lot of scenarios where this doesn't work. Corporate NATs tend to do the thing where they only open that port for one IP, for one external IP, and then they reuse it for a different internal to external communication thing. And that means that if you ping the Stun server, now you have a communication channel open to the Stun server, but that won't work for your peer. So a turn server lets me open a UDP connection to a server. So now I have a stream flowing with this server, and then the server sends me back, instead of the address where I was talking to it, which is what the Stun server sends me, it opens up on its own public IP another port, and then just says, whatever packets come to this port on my public IP, I'll send back to you from through the communication channel that we already opened. So it's relaying. And this solves your NAT problem at the expense of a little bit of latency and quite a bit of bandwidth for the provider, especially if you're doing media streaming. So it's very easy to find public Stun servers, because it's literally like the standard use case is like, I send it a UDP packet, it sends me a UDP packet, we're done.
Yeah.
Right. It's not a high overhead thing to run. You won't find any public turn servers, and if you do, you should say, hey, your turn server relay's open, you might want to shut it off.
Yeah.
Because all of your traffic has to flow through the turn server. Just like on Urbit, if your NAT is giving your planet trouble, all of your traffic has to flow through right now your galaxy, which is why if you have NAT trouble, your Urbit will still work eventually, but it'll be really, really slow.
Yep.
Right?
Yep.
So turn servers are the galaxy relay case for other peer-to-peer infrastructure.
Okay. Great. So that's helpful context, I think, in understanding how we'd answer this next question from Joe. How hard would it be to write Urbit native ICE servers?
In principle, not hard. You would just have to be able to open a more general UDP socket from Urbit. And in the case of the turn server, Urbit would have to actually handle live relay of UDP packets, at which point I'm more interested in how can I actually implement media streaming over Urbit, as opposed to using it as a side channel for existing technology. But that's really, again, in principle, all a Stun server has to do is get a packet in and then take the source address of that packet and stick it in the body of its reply and send it back.
Yeah. Yeah. So Stun seems actually fairly low hanging. Like that's actually something that could just be done.
Right.
Turn, on the other hand, unless we find a good way to bypass the event log, we're not going to be streaming data over AIMS. So that's kind of that's the crux of the problem there.
Right.
So Joe, hopefully you can figure this one out. All right, let's see here. What else we got? Apparently, you do need to write some articles on the Urbit docs.
Yes, I agree.
So that's true. Here's one from Nick. Does WebRTC provide for scaling to many live viewers in a native way? Will the number of viewers be limited by upload bandwidth?
So yes, it will be limited by upload bandwidth. No, it doesn't provide it for you. WebRTC actually provides very little for you, as you've seen. Like, it doesn't even provide call setup and teardown for you. You have to build that. which is why I built it. So the usual setup for something like this using WebRTC, even for like high member count video chats, is that somebody actually runs something that speaks the WebRTC protocol but is not a browser that everybody opens peer connections to, and then it somehow muxes, compresses the data, renders multiple people's streams into one video frame, something like that. And again, you could do this with Urbit. If you have a WebRTC library for your programming language and an Urbit Airlock library for your programming language, great. You can now build this kind of thing on Urbit. But WebRTC by itself doesn't get you there. WebRTC just gives you peer-to-peer media transit with a nice browser API for the media transit itself. That's it.
Yeah. So a common thing that is needed when you get to, because we have another question coming down here that's related to this, like, will group calls be possible? There's another component in the WebRTC stack that is often added in order to deal with, say, conference calls between many people. And this is because, correct me if I'm wrong, there's a cliff of performance degradation when you get upwards of, I don't know, like 4 to 5 different people on the same call, because they're all talking peer-to-peer, and you've got all these different incoming streams, and then that falls off. And so you need another piece of infrastructure in the middle when you start getting into conference calls. Right. And that's the SFU, the selective forwarding unit.
Right.
Can you tell us a little bit about that?
So that in principle is just like you described. And the way that this would integrate into something like Urbit would again be as a piece of commoditized infrastructure. Some people run SFUs, they'll advertise them to the network, and probably once there's enough people around, you'll pay for use, or they'll be included as part of your subscription to the group or your sponsorship from a star or something like that. And again, your SFU is just another WebRTC application. It speaks the WebRTC protocol. It needs to signal with the browsers the same way that if the browsers are speaking directly, they need to signal with each other. So again, the way to integrate this into Urbit is to write an SFU using a programming language that has a good GPU-enabled or even ASIC-enabled media processing library. Have it talk over the Urbit Airlock to IcePond and Switchboard, and have it speak WebRTC through the programming language's WebRTC library. So this case is enabled by what I've done, but it's not built in to what I've done, if that makes sense. Group calls will be possible, but like Josh said, there'll be a performance cliff. And if you want a sense of this, I don't want to talk down too much, because it works impressively well with an impressive user count, and I'd like to know how they did it, because it's clear they're not using an SFU. But if you've ever used a large video group call in Discord, you can tell that it's a peer-to-peer complete graph, because you'll get this instance where out of 10 people, there's 2 who can't hear each other, but everyone else can hear both of them, right? So their connection broke down, but their connection to everyone else is fine, and everyone else's connection to everyone else is fine. So again, it's very impressive that they make it scale to the size that it does, but I've been in 20-person group calls on Discord, and that problem is almost inevitable at that scale.
Yeah. I feel like I've even seen something like this even with Google Meet, where, if you have a lot of people on a call, there will be a couple of people whose video connections are actually live and everyone else's is frozen as of the last snapshot. It's almost like they're, using that as a scale, a way of scaling this so that you're minimizing the bandwidth. I think that's what's going on.
Yes.
So anyway, once this work is done, you can expect to see another grant up for implementing a selective forwarding unit provider, because that's exactly the kind of thing that we would want to see someone build, so that we can then enable group calls. Does this scaling constraint, does this also come into play if you're doing a broadcast one-to-many? If I wanted to, like stream music over WebRTC in a room or something like that to a bunch of people?
It comes less into play, because it's one-to-many, not many-to-many. So you don't have that combinatorial explosion. Yeah. It really is just a bandwidth issue at that point. There's not a lot of extra processing that has to be done. You're processing the media stream once and then sending it to a whole bunch of people. if your implementation of WebRTC is smart enough to do that, which it should be. You're not, so it really, at that point, it's just a bandwidth issue. So you might want an infrastructure where you send your stream up to a server that's sitting in a data center somewhere and then streams down, a server that you or someone running the commoditized infrastructure controls rather than Big Corp. But it's not quite the same because you don't have this complete graph that gives you n squared points at which can fail, and one of them failing breaks the experience.
Yeah, that's right. So one final question before we go into the room and do, maybe not final question, but one question from me before we go into the room and do the just hang out and shoot the shit. What do you personally want to see built using the work you've done so far?
I really want a nice way to send a really big file. This is something you and I talked about. I want to be able to send a really big file from my laptop to my friend's laptop, not through any intermediary. I don't want to have to upload it to Dropbox and have him download it. I don't want to have it store and forward on an email server. I want to be talking to my friend and say, hey, I've got this thing. But I want to send it to you, but it's a tranche of documents. It's 600 megabytes. So I want to just send it to you. We both have good internet connections. Why can't our computers just send files to each other? That just to start off with, I would love to have that. That's not on my immediate list of things to build, but I would love to see that utility exist.
Yeah. Okay. That's awesome. I think you and I remember talking about that with you. That would cut out a huge problem. It's like, why do I need to store this thing somewhere and use up some storage quota in order just to share it with you and then remember to go and delete it? It circumvents the whole thing.
Right. We're both connected to the same network. Why can't we just do that in 2021?
Yeah, exactly. And I just was prompted to go and check out the conversation going on in Urbit itself in the events discussion. There's some cool stuff going on there, but it looks like Ed is already mocking up voice channels and gated access to voice channels and things in landscape. So,
he works fast. That's great.
He works very fast. Yes. So I hope you can you better keep up with Ed. Anyway, so I think we're about out of questions aside from this one. The answer to which is yes.
Yes.
So I think with that, the next thing that we should do is go. We can close this down. Someone sent Hullum in the Urbit channel there. It's an Urbit community. I want to, right after this, I'll post a link to a Google Meet link which uses WebRTC, which is, on the chopping block long term for doing these kinds of things. So we can all jump in there and hang out. And you can ask Edward some questions related to this or anything else, whatever. A reminder: we do these every 2 weeks. There's going to be another one in 2 more weeks with Tlon developer Liam, who's going to talk about push and pull hooks, which are a pretty integral part of how landscape is built. So we'll have more details on that soon. So watch the Twitter and watch Urbit, watch the usual places. But thank you, Ed. This has been really awesome. I think everyone feels that way. We're very happy you're doing this. There's going to be some really cool stuff happening.
I'm really excited to get to work on this. It's fun to get paid to do it, but it's just fun to do it and to be able to have the time available to just get to work on this is really cool.
Yeah, exactly. All right. Well, here is a link that you can join us at. And with that, we'll call it a day. All right. See you, man. Bye, everyone.